Biofuels are traditionally thought of as direct substitutes to our modern combustible fuels. The Biofuels Project at the University at Buffalo has taken a different perspective, looking to create a biological solar panel. We are specifically refining a fourth-generation biofuel, which produces energy without destroying biomass. Our system uses the algae Chlamondius Rienhardi to produce hydrogen gas using only simple salts and sunlight.
The theory behind our project is to use the algae Chlamondius Rienhardi to produce hydrogen gas in an oxygen and sulfur-deprived environment. A sulfur-deprived environment is important because in the absence of sulfur, a new metabolic pathway is created in which a catalyst iron-iron hydrogenase is now activated. This catalyst is what is responsible for producing the hydrogen gas. However, it is highly oxygen sensitive, hence why we need to deprive the system of oxygen. One of the key constraints of our theory is sulfur deprivation. The idea behind depriving the algae of sulfur is that when the algae is subjected to a sulfur and oxygen-deprived environment, the only option for the algae to produce enough ATP or energy is to create hydrogen gas. This is due to the fact that the iron-iron hydrogenase is connected to the electron transport chain and acts as a valve, which allows the algae to survive under oxygen-deprived conditions. So currently we have two different approaches as to how we remove sulfur. The first being that we create our own medium in which we replace the sulfate salts with chloride salts. Another approach that we can use is to grow the algae in a sulfur medium to begin with, since they grow better in a sulfur medium as compared to a sulfur-free medium. Then we can centrifuge these cells out once they have grown, and then we can wash them with the chloride salts in order to remove the sulfur.
An oxygen concentration above 90 micromolar breaks down iron-iron hydrogenase, the protein responsible for producing hydrogen. However, oxygen is produced by the algae. Therefore, oxygen must be removed at a low molarity to continue productivity. Cell media enters the absorption column through dialysis tubing. The oxygen in the cell media will permeate through the tubing, driven by the high to low oxygen concentration gradient, as the algae that is too large to permeate stays inside the tubing. The oxygen will react with iron powder, removing the oxygen from the solution, creating iron oxides, and maintaining the driving force. To measure hydrogen gas production, we plan to saturate the solution with hydrogen gas. This will prevent any further hydrogen from being dissolved, allowing all produced hydrogen to be released as a gas. This allows for lower levels of hydrogen gas to be recorded to greater degrees of accuracy.
For the success of our project, prototyping is a key for a number of reasons. First off, some of the components we need are difficult to find. For instance, the given grow chamber in the bottom right corner of the page had to be prototyped because we were unable to find a grow chamber for algae that met our specifications. Secondly, the cost of some components has driven us to prototype. Our sensor array that we built has 7 sensors and is able to log the data from all of these sensors into a single text file. We were able to make this sensor array for just under $200, whereas if we were to buy the sensors and their respective transmitters, it would have cost over $1,500. Finally, education goes hand in hand with the process of prototyping and constructing many of our components. From learning how to code microcomputers to 3D modeling and printing, education has been a central pillar to this project. Since the start of the project, we have been trying to create our own bioreactor because those on the market were out of our budget range. However, we were fortunate that the CBE department at UB donated a bioreactor with many of the functions we were hoping to recreate with the sensor array we built.
From the experiments we have designed, 2 of which are of the highest importance. The light burst experiment involves selecting algae cells with a lower quantity of pigment. Less pigment in the cells leads to a higher solar energy conversion, and by using high-intensity light, we can eliminate these cells with more pigment. The sulfur experiment involves seeing how our algae will react to removing sulfur from the cell growth media and how this affects cell growth. Many of the experiments which we have designed were originally planned to be conducted this semester. However, that has not been the case and they've been rescheduled for next semester. For our system design, our system operates primarily by removing oxygen in our iron bed and then recirculating the algae cells. The end cap shown here on the right is key for interfacing the dialysis tubing we are using for oxygen transfer with the absorption column. Other inputs to our bioreactor includes our batch reactor for inoculation, light, and our sensor array. Here are some of the citations we've used throughout this presentation. If you have any questions or suggestions, we'd love to hear them. Thank you.